Hello and welcome back to the channel. Take a moment and look around you. The light you're using, the device you're watching this on, the very fabric of our modern world, it all runs on energy. But our current energy sources come with a heavy price: climate change, pollution, and finite resources. What if we could change that? What if we could tap into a power source that is clean, virtually inexhaustible, and fundamentally safe? What if we could build a star on Earth? Today, we're diving deep into the ultimate quest for sustainable power: nuclear fusion. This isn't science fiction. This is the science that could define the future of humanity. So, what exactly is this magical-sounding process? At its heart, nuclear fusion is the same cosmic engine that powers our sun and every star in the universe. It's the polar opposite of the nuclear power we use today, which is called fission. Nuclear fission works by splitting a large, heavy, and unstable atom like uranium-235 into smaller pieces. When it splits, it releases a tremendous amount of energy, but it also produces radioactive waste that remains dangerous for thousands of years. Fusion, on the other hand, does the exact opposite. It takes two very light atoms, typically isotopes of hydrogen called deuterium and tritium, and under immense heat and pressure, fuses them together. When they combine, they form a slightly heavier atom, in this case helium, the same harmless gas you find in party balloons, and a spare neutron. The incredible part is that the mass of the resulting helium and neutron is slightly than the mass of the original two hydrogen atoms. That tiny bit of lost mass is converted directly into a colossal amount of energy, all thanks to Einstein's famous equation, E equals mc squared. Because c, the speed of light, is such a massive number, even a minuscule amount of mass, m, creates an enormous amount of energy, E. To put it in perspective, the fusion fuel in a single glass of water could theoretically produce as much energy as burning a whole tanker of oil. And the fuel itself? Deuterium can be extracted from seawater, and tritium can be produced from lithium, which is also abundant in the Earth's crust. This is what we mean by virtually limitless energy. The environmental benefits are staggering. Fusion produces zero carbon dioxide or other greenhouse gases. The primary byproduct is inert helium. While the process does create some short-lived radioactive material from neutrons interacting with the reactor components, this material decays to safe levels within a century, not millennia. It's a completely different class of waste problem. Furthermore, a large-scale fusion meltdown is physically impossible. A fission reactor requires complex control systems to prevent a runaway chain reaction. A fusion reaction, however, is an incredibly delicate, precision-engineered event. If there's any disturbance or failure, the reaction simply stops. The fire goes out. It's inherently safe. So, if fusion is so perfect, limitless fuel, no carbon emissions, no long-lived waste, and inherently safe, why aren't we all using it right now? Well, that's because building a star on Earth is, as you might imagine, monumentally difficult. We need to overcome two primary challenges that push the boundaries of modern science and engineering. The first is temperature. To force those hydrogen nuclei to fuse, we need to overcome their natural tendency to repel each other, a force called the Coulomb barrier. To do that, we have to get them moving so incredibly fast that they can't help but collide and merge. This requires temperatures of over 100 million degrees Celsius. That's more than 6 times hotter than the core of the sun. At this temperature, matter doesn't exist as a solid, liquid, or gas. It becomes the fourth state of matter, plasma. This superheated, electrically charged gas is a chaotic swirl of ions and electrons. This brings us to the second and perhaps greatest challenge, containment. How do you hold something that is 6 times hotter than the sun? No physical material can withstand that temperature. If this plasma touched the walls of a reactor, it would instantly vaporize them and, in the process, cool down itself, extinguishing the reaction. The solution is as brilliant as it is complex. We hold the plasma in a magnetic bottle. The most common design for this is a device called a tokamak, a Russian acronym for a toroidal chamber with magnetic coils. Imagine a giant hollow donut. We inject the hydrogen fuel into this donut-shaped vacuum chamber and then use a set of incredibly powerful superconducting magnets to create a twisting, invisible magnetic cage. This cage traps the charged particles of the plasma, suspending them in the center of the chamber, preventing them from ever touching the walls. This is the principle behind the largest science experiment in human history, ITER, which stands for International Thermonuclear Experimental Reactor, currently being built in the south of France. ITER is a massive global collaboration, a testament to what humanity can achieve when we work together. Its goal isn't to generate electricity for the grid, but to prove that we can create and sustain a fusion reaction that produces significantly more energy than it consumes, the holy grail known as net energy gain. Specifically, ITER aims to produce 500 megawatts of thermal power from an input of just 50 megawatts, a 10-fold return on energy investment. And while ITER is the flagship, the field is buzzing with progress. In late 2022, scientists at the National Ignition Facility in the U.S. achieved a historic breakthrough, using the world's most powerful lasers to blast a tiny pellet of fuel, creating a fusion reaction that, for the first time, produced more energy than the lasers delivered to the target. It was a monumental proof of concept. Meanwhile, the jet tokamak in the UK, a precursor to ITER, has been consistently breaking its own energy output records. And beyond these massive government-funded projects, a new wave of agile private fusion companies is emerging, experimenting with new magnet technologies and more compact reactor designs, accelerating the pace of innovation. We are closer than ever before. The challenges remain immense. We still need to develop materials that can withstand the neutron bombardment for decades and figure out how to efficiently breed our own tritium fuel. But for the first time in the 70-year history of fusion research, the question is shifting from if we can achieve fusion energy to when. The long-term vision is a world powered by a network of fusion plants, providing a constant, reliable baseload of clean power, complementing intermittent renewables like solar and wind. It's a future free from the geopolitical struggles over fossil fuels, a future with cleaner air, and a stable climate for generations to come. The journey is long, but the destination, a star of our own, is worth every step. Thank you so much for joining us on this deep dive into the future of energy. The quest for fusion is one of the most exciting and important scientific endeavors of our time. What are your thoughts on fusion energy? Do you believe it's the key to our sustainable future? Let us know down in the comments below. If you found this video insightful and want to see more explorations of the science that is shaping our world, please give this video a thumbs up, share it with a friend, and don't forget to subscribe and hit that notification bell so you never miss an update. Thanks for watching, and we'll see you in the next one.